Hello my dear wonderful genius students, I'm back again with a new video. This is lecture number 19 on complex analysis, and from today onwards I'm going to start the contents of module number 3. First, let me talk about what are the topics that I'll be covering today. The main topic that I'm going to teach you is power series expansion of a complex function f of z. Then I will talk about under what conditions a power series is said to be convergent and under what conditions a power series is said to be divergent. Then I will define what is radius of convergence and what is region of convergence. Finally, I will solve some numerical problems for finding radius of convergence and region of convergence. So, without wasting time, let's get started. Students, any function f of z can be expanded about z equal to z naught as follows. F of z is equal to summation n goes from 0 to infinity a n into z minus z naught whole to the power n. Now, let us write different terms of this series. The first term will be a naught, second term will be a1 into z minus z naught, third term will be a2 into z minus z naught whole square plus dot 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 plus a n into z minus z naught whole to the power n plus dot dot dot. Suppose this is equation number 1. Here a naught, a1, a2 dot dot a n are known as the coefficient of the power series, and z naught, that means this one, is known as the center of the power series. Now let us consider one special case where we are going to expand f of z about the origin, that means about z naught equal to 0. So in this case, equation 1 will take the following form. F of z is equal to summation n goes from 0 to infinity a n into z to the power n. Again, let us write different terms of this series. First term will be a naught, second term will be a1 into z, third term will be a2 into z square plus dot 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 plus a n into z to the power n plus dot dot dot. Suppose this is equation number 2. The next topic that I am going to discuss is under what conditions this power series is said to be convergent. Students, this power series is said to be convergent at some point z if it satisfies two conditions. First condition is that the sum of the series about that point has to be finite, and second condition is that this function f of z has to be analytic about that point. By analytic, I mean to say that this function f of z has to be continuous and differentiable about that point, or we can say that this function f of z should satisfy CR equations about that point. Next, let us learn under what conditions this power series is said to be divergent. Students, this power series is said to be divergent at some point z if it satisfies two conditions. First condition is that the sum of the series about that point has to be infinite, and second condition is that this function f of z is not analytic about that point. Now let me define two very important terms. First one is radius of convergence and the second one is region of convergence. Students, if we draw a largest possible circle such that within this circle at all points the function f of z is analytic, then the radius of the circle is known as the radius of convergence, and the region modulus of z minus z naught less than r is known as the region of convergence, where z naught is the center of the circle. Some important points. First one, at all points within this circle, that means modulus of z minus z naught less than r, the function f of z is analytic. Second point, at all points on the perimeter of the circle, that means modulus of z minus z naught equal to r, the function f of z may or may not be analytic. That means at some points the function f of z will be analytic, and at some points the function f of z will not be analytic. The Third one is at all points outside this circle, that means modulus of z minus z naught greater than r, the function f of z may or may not be analytic. That means at some points this function f of z will be analytic, and at some points this function f of z will not be analytic. Here these cross marks represents the points at which the function f of z is not analytic, and these dot points represents the points where f of z will be analytic. Now let us learn how to calculate the radius of convergence. Students, we can calculate the radius of convergence by two methods. First one is by using formula, and second one is by singular point method. Formula number 1. The radius of convergence r is given by limit n tends to infinity modulus of a n divided by a n plus 1, where a n is the nth term in the expansion, this one, and a n plus 1 is the n plus 1th term in the expansion, this one. Formula number 2. 1 by r is equal to limit n tends to infinity modulus of a n whole to the power 1 by n. However, this formula is very rarely used. So this is all about today's video, and I hope that you have learned a lot from this video. The numerical problems will be done in my next lecture.